section 4.1, the first part of it. We are going to deal with what we call the initial value problem, and we will come back and also talk about the boundary value problem. So this starts with initial value problem. Initial value problem. We're gonna abbreviate with IVPs, initial value problems. So recall the nth order linear differential equation written in the form a sub n x d the nth derivative with respect to x plus a n minus 1 of x the nth minus 1th y derivative x n minus 1 plus da 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 plus a1 of x dy dx plus a0 of x y equals g of x. So all these a sub n's, a sub n minus 1 all the way to a0, those are coefficients. G of x is a function, and the other ones are derivatives. So before we did mostly first order differential equations. Here we're going to study in this second or higher order differential equations. And this kind of differential equations are subject to the initial condition or initial conditions defined as y of x0 equals y0, y prime of x0 equals y1, y double prime of x0 equals y2, all the way down to the y to the nth minus 1 derivative of x0 equals y sub n minus 1. Notice we have n conditions. So actually, since it's an nth order differential equation, so we have n conditions. N conditions are involved. So the initial value problem, the conditions are given in this format: y, y prime, y double prime, all the way up to y the nth minus 1 prime. These are different conditions on the differential equation. Later on, we'll see the boundary value problem. The conditions are slightly different. They don't involve derivatives. And that's how you're going to know that, oh, is this initial value problem or this is a boundary value problem? That will help you to find out. So what we do here, we try to look for solutions containing x sub 0 satisfying the above conditions, n conditions, and conditions on some interval, call it I. Now what I just mentioned, if the conditions look like y of x0 equals y0, y x1 equals y1, all the way down to y xn minus 1 equals y n minus 1, if the conditions in that form, then it is called a boundary value problem. Now, when we solve a second or higher degree differential equation, one thing very important in mathematics, one thing we have in math is when we find a solution, is that solution unique or not? Is it a unique or not? That creates something called existence of unique solutions. So what is the existence of the unique solution? How do we test if the solutions are unique? So several conditions first need to be met. Okay, we let all these ones I mentioned earlier, an minus 1x, da da da, a1x, a sub 0x, these are coefficients, and including the function on the right side, which we call the g of x, let those all be continuous. This is just a part of the conditions, continuous on the interval I, provided that the leading coefficient is not 0 for all x in I. So the leading coefficient cannot be 0. So in case x0 in I, then a solution to the IVP, you know what IVP, initial value problem, the IVP above, the solution exists and unique on I. When you see the first example, you will know what this is all about. This example is from the textbook. Let y equals 3e to the 2x plus e negative 2x minus 3x. Let this be a solution to the IVP initial value problem, y double prime minus 4y equals 12x, with the given conditions y of 0 is 4 and y prime of 0 is 1. So the first thing I want to comment on this, later on throughout the lessons we will teach you how to solve this, where they got this from, the 3e to the 2x plus e negative 2x minus 3x. Why is that a solution? It's not guess and check. There's methods for that. We will teach you this. It's fun to learn. So what are the conditions that we need to check to prove the uniqueness here? So what we're trying to do is we need to check, is this solution unique or not? They tell us this is the solution, but we don't know if it's unique. So to check for uniqueness, we need to take the coefficients 1, negative 4. So the coefficients 1 and negative 4 are what? Continuous. Also, the g of x, which is 12x, it's a linear function, is also continuous. So we need to check continuity. And the last one, of course, both of them are on over all real numbers, continuous. And we need to check the leading coefficient, a sub n. In this case it's 1, it's not 0. As long as it's not 0, since these conditions are met, then the given y is unique. It's a unique solution. And notice this is initial value problem. You can tell from the condition. There's y of something equals 4, then y prime. So that tells you it's a initial value problem. If we look at another example, also from the book, but I modified it a little bit. So this is a given differential equation, has y equals cx squared. I just kept it as c. This as a solution. This is a solution. Is it unique? Well, let's check that out. What are the coefficients? This, and this. So x squared, negative 2x, and 2. Are they continuous? Yes, they are continuous over all real numbers. How about the 6? G of x equals 6 is continuous as well. One more condition. Is the leading coefficient not 0? Is x squared not 0? Well, it can be 0. Note, it can be 0 when x is 0, which violates one of the conditions for the existence theorem. The existence theorem. So what we say, look what I'm going to say. Y may not, not exactly not, but may not be unique. May not be unique. So note, in this, in the initial value problem, when we say, a lot of people don't think twice about this. We said this is a solution to that differential equation. That solution is actually a curve, right? Back in elementary school, when we found the solution for a linear equation, it was just a point, like a number, one number. And later on, when we learned quadratic, it was 2 numbers, and so on and so forth. But here in differential equations, the solutions are basically curves. And one thing about the initial value problem, this solution must go through this point, 0, 4, right? Not 0, 1, not 0, 1, because that's a derivative. Okay, just keep that in mind. And now I'm going to do the boundary value problem. BVP. So those are differential equations with order 2 or greater. With order 2 or greater. So what are the solutions? That's what we're going to do here. Solutions to the BVPs. Well, it will have conditions in this form. x0, y0, x1, y1, all the way down to xn minus 1, yn minus 1. See, no derivatives. And all these are just n conditions or n given points for the initial value problem. Now, in the difference between the boundary value problem and the initial value problem is that when we have the initial value problem, you can have curves like this, let's say, as solutions. And in the initial value problem, the first one we talked about, it must go through the first point, x0, y0. But in this case here, for this kind of boundary value problem, which curve is considered as a solution? Is it all of them or only one of them? So which curve is the solution for the boundary value problem? Again, for IVP, the curve must go through x0, y0 only. But in the PVP, the curve must contain all the points. You know what all the points? All the points x0, y0, x1, y1, all the way to xn minus 1, yn minus 1. So maybe if the first curve is the solution, these points I just wrote down, they all must contain, they must all be on that curve.
So does that mean it doesn't have a unique solution?
It doesn't have what?
The unique solution?
It does have a unique solution. This is the unique solution, the one that goes through all these points. So how do we apply this? Again, as I said, later on, we will see how to solve these kind of equations. So differential equations. Consider the boundary value problem, y double prime plus 16y equals 0, with y of 0 is 0 and y of pi over 2 equals 0. And the solution to this differential equation, which will teach you how to get it later on, is given by y equals c1 cosine 4x plus c2 sine 4x. What we want to see here, to look up if this has a unique solution, this specific one, or not. How do we check this? Well, or is there only one solution, or infinite number of solutions, or n solutions? So we need to find C1 and C2, because the values of C1 and C2, they tell us how many solutions there are. So what is basically C1? What is C2? Well, let's look at the first condition. Y of 0 equals 0. That's the first condition. If we substitute it into the solution function, we get 0 equals C1 cosine 0 plus C2 sine 0. So 0 equals sine 0 is 0, and this is cosine 0 is 1. So I found C1. How about the second condition? C of pi over 2 is 0. So you get 0 equals C1 cosine pi over 2 plus C2 sine pi over 2. And what do we get for that? 0 equals cosine pi over 2 is 0. This is gone. Sine pi over 2 is 1. So C2 is also, right? C2 is also, oh, no, wait. It's not pi over 2. We substituted wrong. Because x is pi over 2, but there's 4x in there. 4 times pi over 2. So 4 times pi over 2. 4 times pi over 2. So that's a 2 pi. That cosine 2 pi is 1. So that's C1 times 1 plus C2 times 0. So again, C1 is 0. So from the two conditions, I got C1 0. So what about C2? What happened to C2? Well, C2 can be any. That's what this means. So that solution that we have, since C2 is any and C1 is 0, then y comes down to C2 sine 4x, because C1 is 0. So that tells us that there's infinite number of solutions. Infinite numbers of solutions containing the points 0, 0 and pi over 2, 0. Does that make sense now about the existence of the... And I can show you even graphically what that means. So if we graph this function y equals c2 sine x, 0, 0 is here. Say pi over 2 is 0, pi over 2 0 here. This is a sine function. So what happened? Why do we have infinitely many? Because of c2, depending on c2. c2 tells us the amplitude. So it can go like this and then down, and then maybe it can go this and down, or this and down, or this and down. See, that's why there's infinitely many of them. So for the boundary value problem, we can write a note for boundary value problem when the conditions are met. The conditions are met for the existence, then unlike the initial value problem, there could be several solutions, or there could be unique solution, or none. So it's kind of like an open thing. Anyone has any questions about this part?